Thanks everybody for attending the November 2021 meeting of the Raleigh Astronomy Club. And do want to ask that once we get started with our conversation or with the topic, if folks can go on mute, just to be respectful of the speakers. So again, welcome everybody. Especially a big welcome to all of our first-time members. We've had a lot of folks joining the club, so definitely welcome. And any relatively new members and guests, feel free to, if you want, post your name in the chat. Let us know how you found us, if you'd like to. And again, thank you for being with us. We're going to do a little bit change of pace for this session. Typically, we would do astronomy days as part of the business update, but because it is important and we did want to kind of get it recorded for other members to see it, we're going to just do a few minutes of it right now before the presentation on deadly spheres. So we will go ahead and jump right into that. Astronomy Days 2022, that will be held on the 29th and the 30th of January. And this year's theme is Venus. So that was picked by the museum. This is RAC's signature event for the year. We originally started this event, I don't know, 25 some odd years ago or even more, and it has expanded from just being one day in a shopping mall at Crabtree Valley Mall into now being a week-end event at the Museum of Natural Sciences. We have lots of other folks that help us put this program on, including it's supported by NASA and many other local astronomy-related organizations, the Moorhead Planetarium and Science Center, Chaos, et cetera, et cetera. So it is a fantastic event. And this year, last year it was virtual, but this year it is going to be, oh, by the way, and we do draw quite a few people. So on average, we've been drawing somewhere in the neighborhood of over 14,000 visitors to the museum over a 2-day period. We are hoping that 2022 will be a face-to-face event. So that is what we're planning on. There is going to be some limited space on the first floor of the NRC building, which is, if folks are familiar with the museum, it's the newer of the buildings because of some remodeling. So we'll have to move some of the exhibits that are traditionally there, such as astrophotography and potentially telescopes on display. Masks will be required for staff and for any volunteers. Mask requirements for guests are still to be determined, and it all depends on what the guidelines will be at that time for the city of Raleigh, the county of Wake, and so forth. So that still is up in the air. We will be supporting exhibits as well as seeing if anybody wants to do presentations / talks during the weekend. And new this year, we are going to have an associated star party the following Saturday. And folks may have seen that if you're part of the outreach groups within the Groups.io platform. You probably saw Matt's posting that today, but this will be something that will be promoted during Astronomy Days and hopefully will be a great event over in Prairie Ridge the following Saturday. So what do we do typically for Astronomy Days? We have various exhibits that we put together. One of them that we do typically is the the RAC table, or come meet the Raleigh Astronomy Club, as well as Ask the Astronomer. So this is just generic information about the club and folks to ask questions. We also do telescopes on display, and this is always a great opportunity to showcase some of your equipment. We've done things like challenge at the eyepiece, where we've hung certain objects, photographs inside the building in the past, and have people try and locate them through telescopes. We've got some phenomenal work from our imagers at the astrophotography exhibit. And we've also done in the past exoplanets. So where we've had some exoplanet models, we'll have a Drake simulation or Drake equation simulation, as well as a Lego orrery that shows how Kepler finds transiting planets or exoplanets. We've done solar observing outside. And we've also done, and this is always a great big hit with the kids, age, weight, and jumping on other planets. So these are the typical exhibits that we've done in the past. We're on the fence about whether to try and add any more exhibits. Again, I think coming back from the having it all virtual last year, and then again, COVID will still be a potential issue. Not sure how many volunteers or supporters we're going to get, so we don't want to spread ourselves too thin. But those are the exhibits that we'll typically do, and then we will ask for people to definitely, if you can, support the actual day of the event. We always ask for folks to consider volunteering for one of the 3-hour shifts during the weekend. There are 5 in total, 3 on Saturday, 2 on Sunday, and those times listed. And if you do volunteer and you want to be part of the RAC volunteer apparel program, you get this nifty shirt, which also has some information on the back. We also, if anyone wants to do a talk, if there's something that they're passionate about and want to share that with the public, they're always open for speakers. Usually you get 1 slot on Saturday and 1 slot on Sunday. We could definitely use help with some of the exhibit leads. Again, most of this stuff has already been put together. It's really being that point of contact on the day of the event and making sure we have all the materials ready. Also, volunteer coordinator is always great to have to make sure when people volunteer, we know where to send them and see what exhibits need help. And of course, we will be looking for Star Party volunteers the following Saturday to bring out scopes and share views of the night sky. So with that, that is the Astronomy Days portion. Open it up if folks want to ask any questions about Astronomy Days.
Hey, Mike, it's Doug. I want to interject. For many of you who are new in the club, this would be like your first Astronomy Days or whatever. And I just want to encourage you to take the plunge and volunteer. Now, we won't put you to with or put you out alone, leave you hanging for the wolves to chew at you. But we'll always pair you up with somebody who is an experienced observer or experienced in the astronomy club. And it's a great opportunity. I found even when I was new in the club, it was a great opportunity to actually learn something and actually get better as an astronomer, to get some good knowledge. So definitely want to encourage everybody to do that. And also too, if you just, I think Amy really brought this out in our last session. But if you don't know the answer to something, say, I really don't know the answer to that question. Not really sure what the answer might be, but go see, Mike or Doug or, Steve Christensen. Well, there are people that you can go and talk to who will be able to answer your question. And we have the Ask Astronomers booth up there, and you can always afford people there. So we're not going to leave you hanging. It's a lot of fun. Believe me, you're going to come back pumped and really excited about astronomy, and even more excited to kind of put your skills to use at the Star Party the next week. So I just want to encourage everybody just to sign up, and this is a really fun event.
And each year we go ahead.
I think they also give us a free lunch if you do 2 shifts. Is that still the case?
I believe it will be, yes. And then we always have a script written, or at least some information at the table for general information. Some of it will just be general club stuff. But if you're doing one of, I know for the Lego or Area 1 and age, weight, and jumping. We've got scripts written that kind of walk you through everything, but there's usually someone there that can help you as well. So we'll be sending out more information shortly with regards to how you can volunteer for the event and sign up. So please be on the lookout. So
There's a chance I actually might be able to make it out there for that since I'll be retired. So
All right.
rub it in, John.
I gotta work on our lodging and stuff, because I'd be out of town. But
Wait, you got a camper, man.
I'm sure it would be fun blocking that NRC parking deck if I drove the RV there. Yeah, that would be awesome.
That might be interesting, getting that RV in the local parking deck.
So there are 2 questions in the chat.
Yep.
And I think they've been answered, but maybe we should announce it to everyone else. So Prairie Ridge is the star party that will happen. It'll be at Prairie Ridge that will happen the next Saturday after Astronomy Days. Is that correct? And that is what Steve said. He said that was correct. And then are we sending out a link to volunteer? I can never remember.
We will, yes.
Oh, okay. So we volunteer, and then don't volunteer, I guess, with the with the museum, because we have a special volunteer list for us.
Exactly.
I mean, I guess you can, but there's a special volunteer list for us. So don't get confused.
So we'll be sending out more information in the next week or so with regards to kind of all that information. So.
And is there a deadline for the, if you want to have a talk ready, should we if we have a topic, who should we send that to?
So I think we just got some of the information today.
Right.
So we'll be sending out an announcement as well.
Oh, okay.
It'll have that. Yeah. We literally hot off the presses.
Yeah, we just got it today, and generally though, it's we have up to, I think, December 2nd or 12th, something
usually,
like that.
Yeah.
Before that's the cutoff for the club before they open it up to the SSAs and to the general public. So you don't have to have your talk ready, just a subject in mind and then a description of your talk. So.
Yep. Okay.
And that's all you need until the day you actually give your talk.
And are we doing a Friday talk at all? Sometimes in the past we've had, but I know this is kind of a weird time. I don't know if we're gonna have a Friday evening talk.
That is up. We're still up in the air. We don't know who some of the keynote speakers are going to be. So and who we'll have available. So still to come. They are hoping to get an astronaut to come.
Oh, good. Okay.
Yes. So, okay. Well, with that, unless we have any other questions, Doug, I will turn it over to you.
Okay, great. Thanks, Mike. Appreciate that. All right. I think I've got. Let me just adjust my.
And then, so, Doug, you want people to go ahead and kind of either post questions in chat or wait until the end, right?
Yeah, if you guys could do that. I've got a lot of slides to go through, and I'd like to try and get through all the slides before answering questions. So go ahead and post those questions to the chat, and then we'll try to get to all those later. Maybe if someone could monitor the chat and everything, and then at the end, guide me through it. So, all right, that'd be great. All right, are we ready? All right, I'm going to take that as a yes. All right, good evening, everybody. My name is Doug Lively, and as you may have seen from Mike's description, I'm an SSA with Raleigh Astronomy Club. I've been a member of the club for, goodness, about 25 years, and have got several observing awards. We're going to talk about observing awards at the end of tonight's business meeting. So if you're interested in earning an observing award, please hang around. We're going to have some great information on how to do that, and a special surprise introduction from one of our long-term club members on awards. So anyway, again, welcome. Tonight is the second installment in my Death and Destruction Kill the Rabbit series, and it's called Deadly Spheres, the top 10 ways the solar system can kill, maim, or really, really hurt you. And so this is really just a kind of a fun look at some of the things that are lurking around in our solar system, things that that could be deadly if they did occur. But I will tell you, there is some real research behind this. I actually, for those of you who are in quality and you understand the term FMEA, I actually performed an FMEA on each one of the topics tonight, the subtopics in this Deadly Spheres program. So there is a real consequence that can occur, and I've actually leveled a risk assessment against what those are. So, but we won't be actually talking about that risk assessment because people have a tendency to kind of roll their eyes back in their head and then like fall asleep. So tonight we're just going to take a great fun look at our solar system and its structure. You know, the one thing that's really cool about science and especially about our solar system is that our information has grown exponentially over the last 75 years about the structure of our solar system, the elements and inhabitants of our solar system, if you can say that. And so we're going to look at some of the things that that have changed over the years, and then look at what's happening now, and then kind of look to the future. So that's really what we're going to do with this program tonight. And I hope, like I said, put your questions in chat and hang on because we're going to go quick. So here we go. All right, first thing I want to do is kind of talk about.
Doug, are you sharing your screen?
I'm probably not. Well, it's good because it's the first slide. Share should be starting right now.
Yep. Thank you.
All right, can everybody see that? All right. So the first thing I kind of want to point out is that our address is now planet Earth, Orion Spur, Perseus Arm, and the Milky Way. 75 years ago, and we didn't know where we were, but we're there. And this is kind of superimposed on top of an artist's conception of our galaxy, the Milky Way, which is theorized relatively strongly that it is a spiral bar galaxy. That's this bar structure that we kind of have in the center here. And that we're sitting out here on this, the main spur of the Sagittarius arm. There's the Orion spur. And our sun's located about roughly 2/3 of the way out from that, although according to an article earlier this year, we're actually just slightly closer than what we first theorized. And that's one of the things that we're going to talk about tonight, is that our information about where we're at in our galaxy, where we're at in our universe, where we're at in our solar system has been changing. It's been changing a lot. And a lot of times we don't take that look back to say, well, hey, where we come from? And again, 75 years ago, we really weren't sure where the sun's position was. We weren't even sure that the Milky Way was near us, you know, and so thanks to Lowell, we've actually been able to find out and realize that, yeah, we're actually sitting in the Milky Way. We're part of a galaxy, and then other galaxies like Andromeda and such are outside of our galaxy. So these are just things that we just didn't realize, you know, again, roughly 75 to 70 years ago. So this is all new information, relatively new with respect to astronomy. So the next thing I want to talk about is your granddaddy's solar system. So I can tell you that because this is what your granddaddy's solar system looked like. Now, for some of you who are my age or older, maybe not, maybe it was different, but when I'm actually a grandfather, in fact, I'm a great grandfather, and this is the map that was hanging on my wall when I was about 9 years old. And in those days, we hadn't even sent one probe to one planet. We had the Mariner projects and the Viking projects that were basically, you know, taking pictures of the moon and stuff like that. But those were very primitive. If you look up here, here is an artist's conception of Sirius. Now, how right were they on that? Not very, because we know that Sirius is a sphere, and it's spherical, and it's a dwarf planet. We really didn't realize, we didn't really understand what, you know, hydrostatic compression was, and that how bodies, once they reached a certain point, actually begin to form into a sphere. They just saw Ceres as kind of this oblong asteroid. So there was very poor understanding of what asteroids looked like. Same way with the rest of the solar system. In the 1960s, space was sterile. It was a vacuum. Nothing really happened. Occasionally we'd see a comet, but that was about it, you know. And so it was a very static, unchanging entity. And so it was a considered not very interesting to look at. Now, of course, today now we have spaceweather.com where we're seeing all kinds of interesting things happening that interacting between the Earth, the Sun, and the Moon. Today, we now have a much better understanding of how our solar system is arranged. And again, not only do we have the asteroid belt, but this idea of the Kuiper Belt and the Oort cloud were only theories in the 1920s. We didn't really have proof that the Kuiper Belt existed until 1992, and then the Oort cloud itself was not really verified till much later. So we have this really interesting arrangement now in our solar system. Another interesting thing about our planets is that it wasn't really well understood then. Was really this the thing that the large outer planets do for our inner planets. So as we actually, if you can see right here in the right hand side of my screen, we have a comet coming in. There's also one down here, but they're actually coming in and they're actually being deflected in towards the gas giants. So the outer planets, Neptune, Uranus, Saturn, and Jupiter, actually serve as gravitational shields for our Earth. So anything coming into our solar system actually kind of comes along, gets aligned in accordance with this gravitational attraction, and actually is either deflected out of our solar system in a hyperbolic orbit, or into a parabolic orbit where it either goes into the sun or comes around the sun. And as it comes around the sun, then it has to interact with Mercury, Venus, and the moon. And the moon itself is roughly the size of a small planet. And so it's if you any night you go out and you look at the moon, you can see that there's a lot of craters there. That's really just showing you that the moon is really taking it on the chin for the Earth, because it's really kind of our last defense whenever there's a body coming in that could strike the Earth. So that's one of the things I think that's come out, is understanding that this really unique or ordering of our solar system actually works to preserve life on Earth. I'll also point out that of the exosolar planets and systems that have been discovered, I don't believe one of them actually matches this arrangement. That's our ordering of planets so far is unique. So that if you look at any exoplanet system, generally you have the gas giants are oriented around the sun, and the rocky planets are oriented around are in the outside. And so I think we actually had a talk on this, that we actually had an event that actually somehow actually caused our rocky planets to actually migrate from the outer solar system to the inner solar system, and then the other gas giants actually migrated out. So it's really interesting. We have a very unique organization to our solar system. One that, again, we haven't found yet, but it's not to say it doesn't exist, but it is something that's unique right now. All right, so let's go to the next page. The other thing that's really unique is understanding that the sun is actually orbiting around in our galaxy, that the planets then sometimes follow the Earth and sometimes, follow the sun and sometimes lead the sun. If you looked right here in the lower right hand pane, I can actually start this again. You can see that instead of an elliptical orbit, they're actually following in somewhat of an elliptical spiral. So as the sun moves this way, we're spiraling around the sun this way, following the sun, or actually this way. And then finally over here in the lower left-hand panel, something that we didn't understand was really this, what was the size of our solar system? We did, and we still aren't really quite sure. Some people think it's about 100,000 AU, and an AU is basically one astronomical unit, and that's the distance between the sun and the Earth. That's 93 million miles, so that's one AU. And so the feeling now is, after the Voyager 1 and Voyager 2 spacecraft, which launched in 1972, that they're now in interstellar space. And so the idea is that there's roughly 100,000 AU in the total diameter of our solar system. So that's, again, something that we didn't know. Again, not your granddaddy solar system. And finally, one of the really interesting things is of course the Kuiper Belt. Again, I mentioned that earlier. In the Kuiper Belt, we have we've been able to show that short period comets that occur very regularly, come from the Kuiper Belt. They generally have orbits that are in terms of in tens of years. And so they actually are in this disk-like object here that you might see my cursor floating around, known as the Kuiper Belt. All right, and again, we didn't have proof of this until really 1992. This belt exists roughly about 50 AU begins about 50 AU, begin between 30 AU and 50 AU from the sun. Okay, and then we have this really interesting cloud. It's really kind of a compound cloud known as the Oort cloud, and there's a lot of objects in the Oort cloud, and so this is a cloud that we really haven't explored very much. So the Oort cloud is actually a compound cloud. There's two sections to it. We have the outer Oort cloud, and then there's a toroidal inner cloud underneath this. And so this is what you see kind of in this somewhat toroidal section right here that my cursor is going around. So there's an inner cloud. We have our long period comets actually come from this. So those that are on the order of hundreds of years or more actually orbit in and out of this cloud towards our sun and then back. So and there are also a lot of icy, rocky bodies here that we haven't discovered. In the Kuiper Belt, we are beginning to discover more objects. If you can see here, Pluto's orbit is actually in the Kuiper Belt. So this is one of the reasons why we kind of moved Pluto into the status of dwarf planet. We've discovered, back at, even way back really in the early 2000s, we only had maybe one or two objects that we knew about in Pluto's, when we changed Pluto's designation into a dwarf planet. But now, over the last 20 or so years, we've got about 45 major objects out here in the Kuiper Belt that we deem as dwarf planets, and there are other bodies there that are waiting to be designated as dwarf planets, and it's really just where more discovery, more research needs to be conducted. So that's the Kuiper Belt and the Oort cloud, and these are things that, again, when I was growing up, you never heard about these things because they are only kind of possible theories, but the proof of the pudding and the proof of these things really didn't come to fruition until really only a few years ago. We're talking tens of years that we've even known for sure that these objects actually existed. All right, so let's go to the next. So let's talk about a little bit. The first thing that could maim, kill, or really hurt you is a primordial black hole. So now, what is a primordial black hole? So at Big Bang, it is theorized that at Big Bang there were black holes that were formed. They were large, but if any of you have heard of Stephen Hawking theorized that black holes actually over time can shrink. They can kind of lose that energy. That shrinkage is called Hawking radiation. You may have heard of that. But with respect to this, so is there a primordial black hole possibly in our solar system? So I'll tell you how that came about. So roughly about 2014, we began noticing that there were out in beyond Pluto's orbits orbit, some of the objects in the Kuiper Belt began interacting as though there was a supermassive object out there. So it was theorized, oh wait, that means there must be another planet out there. And so based on this interaction, there are some calculations made. We determined that the orbit of this planet would have basically a diameter of about 200 AU, which again, 200 astronomical units. You just take 200 times 93 million, and you got the number millions of miles that it is. So we thought that there could be a possible massive object out there. And so we thought that that might be Planet 9. And so it really, for the past, again, that was in 2014, the past 7 years, we've been looking for this. And, it really, of course, I did this back last year. So I said after 6 years of intense searching, they're still looking for it. But we're looking for an object that's possibly, 5 Earth masses. And we've been looking for it. And we know mathematically where it's supposed to be, but we can't see it. It should be something about maybe roughly a third of the size of Neptune, but we just can't find it. So the possibility is that we actually don't have a planet out there. It is a real possibility that there is a supermassive object, which would be a primordial black hole. Somehow our Earth has captured a black hole, or sorry, a sun has captured a black hole in its gravitational field, and it's out there orbiting the Earth in a very stable orbit, roughly about 25,000 years. It's a very long orbit. So it's not going to, the chances of it falling into Earth are not very, likely. But I just wanted to kind of show you, here's a couple of supermassive black holes. The one on the right, of course, is M87, which was imaged a couple of years ago. This is the initial image. I understand there's now a much more refined image, which is pretty cool. And the next one, the one that's in the center that you see these stars kind of circling around, is Sagittarius A star. And if you look here to my left, here's a star map, and this is the constellation of Sagittarius. If you look right here, this little teapot structure right here, and just out this way, you can look, the teapot's actually pointing out to where Sagittarius A star is. This is actually the center of our galaxy. And these are, you can see these stars, again, you can't see this black hole, at least not yet. Maybe when JWST, which is the James Webb Telescope, launches, maybe we'll be able to see something a little better than this. But these are stars that are just, you can see them whipping around, and you see them interacting here with objects in the center of our galaxy. This is very much like what we're seeing out in the outer edges of our solar system, but with much smaller objects. These are, of course, these are massive stars that are being whipped around by a black hole. In the case out there with a 5 Earth gravitational mass, you see objects, bright objects from the Kuiper Belt, kind of doing the same sort of thing. So we can see that happening. Again, we can't see a planet, and that's the thing that's concerning. Now, if a supermassive black hole kind of opened up over Earth, again, there's been we continue to do deep sky surveys, and in this lower right-hand picture, you can see as that the space is distorted around this supermassive black hole. So we're continually looking for distortions in space that are near us. So we don't see anything like this that's at least near our solar system. The closest one, again, is like M87, and so it's roughly 1,000 light years away. So we're in pretty good shape. It's not about to gobble up our Earth. But if one did come in, it would kind of look like this. You might see basically our atmosphere and our water and all that being sucked into the black hole first, before it basically then gobbles up our Earth and then begins to kind of stretch our Earth and basically turn it into spaghetti, and then it bifurcates all the way down to the central singularity. That would kind of pretty much spell the end for Earth. But again, for a supermassive black hole, that's not likely. Now, what about a primordial black hole? That's an interesting one. There are a couple of papers out there that talk to whether or not what would happen if again, you've got a primordial black hole, roughly the size of a grapefruit or basketball, with a mass between 5 or 15 Earths. I mean, that's a pretty heavy basketball, right? And so what would happen if it actually hit Earth? Well, there's two scenarios. One, it could just pass through the Earth and not actually absorb the Earth. It would, basically create a lot of destruction and everything where it hit, and then would just pass through the Earth and pop out the other side, leaving another trail of mass and destruction, and then just go on its merry way. But the other scenario is, and this is the worst case, is that it could possibly decide, oh, well, I'll set, if it passed through our core, that would be very bad, because at our core, you basically have the equalization of our gravitational attraction. So it would basically kind of stop at our core. It would begin to consume our core, and then eventually, devour the planet, and that'd be pretty much the end of all of us. But again, this at least according to the current study, this whatever is out there, the thing is roughly 4 to 5 to or so Earth masses, is in a very stable, very long orbit. So none of us are going to be around when the primordial black hole comes to town. So you're in pretty good shape there. So, all right, let's move on to the next one. All right, the next thing is comets. So now comets are a lot more regular. So we've got some really cool looking comets here. We've got the one over here is Comet Hakataki, which is on the right here. This was what kind of the classic comet. If you were around in the late 90s or so, this was a really amazing sight in the night sky. Over on the left, we have Comet Lovejoy. And it was really beautiful. It was a pretty comet, roughly about 4 or 5 years ago. And then last year, I believe it was, last year we had Comet Neowise. This picture down here on the lower right, it was actually taken by our own Mike Keefe, with a cell phone camera. And so it was just a really cool comet. First, it was an early morning comet, then it was a late evening comet. And we had a lot of fun. All of us got really great pictures of it and all kinds of different angles and stuff. So it was a great comet to look at. We actually have another one coming around. I just saw in Sky and Telescope that there's a new comet that's possibly roughly around December 12th. So be looking for that to brighten. And maybe we can have some discussion there, as we go on. So, all right, let's go on. Right, so in a comet, when we're looking at ice and dust. It has basically three main pieces. There is the core or the nuclei of the comet. That's kind of the innermost piece of it, that the substance of the comet. We have a coma, which is kind of a nebulous envelope that forms around the comet as it's being warmed by the sun, and as particles are beginning to strike the surface, it actually kind of causes a coma or kind of a foggy mist to form around it. And then sometimes as the comet approaches Earth, it will actually produce a tail, and it will and that tail can actually be split into two tails. We have the regular comet tail, kind of that you saw in that last picture of Comet Lovejoy. But then sometimes it produces an electrically charged plasma that's coming off of it, which is basically, which we call an ion tail. That's that blue tail. And I'll go back to our prior slide. That's that beautiful blue tail that you see right here on the bottom of this comet. So it was that doesn't happen with all, as you can see, like with Comet Neowise and Comet Lovejoy. We really didn't have that with those comets, but Comet Hakataki actually had that really beautiful ion tail. And there's been a few since then, and some of the other guys in the club who actually image comets, like Mark Lang, and so have some great images of those. So, all right. So anyway, in the core and nuclei, we basically have ice, dust, small rocky particles, mainly silica, clays, rock. We have noted that some of them have a lot of cyanide or oxygen, carbon dioxide, ammonia, methane, lots of heavy metals. So there's a lot of stuff that's, a lot of people feel that comets are part of the leftover building blocks of our solar system. And so they're really interesting objects to study because they kind of represent the primordial solar system that we really never got a chance to observe. Right. Now, with relation to size, okay, so this is basically a comet, and excuse me, I'm really going to hack this name, Churyumov-Gerasimenko. And so this comet was very famous because we sent an orbiter. Actually, the European Union sent an orbiter out to orbit this, and they had a little lander called Philae that kind of didn't quite land correctly, and its harpoons that they thought would actually stick into the ground, they actually didn't. They kind of bounced off of it, and then as the lander came in, it just kind of pounced and bounced a few places, and so they really weren't clear on what this comet was made of. It kind of, if you rotate it the other way, it kind of looks like a little rubber ducky. But what the ESA, which the European Space Agency did, was they took this and they superimposed the actual size against Los Angeles. And you can see that these comets are actually massive. So a lot of people think, well, hey, all we got to do is something like that's coming towards us, we can nuke that. Well, you really can't nuke that. All right, the nuclear device, even the really powerful ones, aren't really strong enough to deflect, cause that to deflect, or to cause it to disintegrate. It's not going to happen. You're going to basically wind up with a radioactive cometary fragments that actually rain down on Earth. So it's really not possible to do that. Roughly about 1994, I know some of the club members that were around at that time were to see Comet Shoemaker-Levy 9. It broke up into really roughly mountain size, about roughly 2 kilometers in diameter chunks. That was really due to Jupiter's gravitational pull. And this is really, again, a demonstration of what our large gas giants do for Earth. First of all, they broke the comet up into roughly, again, about 20 fragments, which was known as the string of pearls. And then it was all aligned with Jupiter's orbit. And the next year, in 1994, it came around again, and each one of these string of pearls basically collided with Jupiter. And when it did, it punched these holes into Jupiter's atmosphere. Okay, and these holes are all determined to be about the size of Earth. So if this had actually been, if we hadn't had Jupiter in place, it very, very well likely could have been us, and it could have actually hit, Earth, and just one of those fragments probably could have really just destroyed the Earth, and we'd really just be particles of clumps of rock floating around in the solar system now. So it's really is a testament to what Jupiter does for our solar system and the other gas giants. But it's also a wake-up call, because really it's 1994, folks. That's 28 years that we've known that, or I'm sorry, 27 years that we've known that we should be doing something about some of these near-Earth asteroids, near-Earth comets, stuff like that. And right now, to this point, we have no deployed or proven technologies that would actually deflect or prevent a comet or a near-Earth asteroid from hitting the Earth. We've been harping on this for almost 30 years now, and we still have nothing. Now we're about to deploy one satellite technology that's about to the DART, which is about to go off and test some technologies for asteroid deflection. But right now, again, we've got a lot of great theories. We had a lot of talk, but we haven't done anything. And so, really, the next thing that comes along, could be the end of the Earth. So, at one point, it's ignorance is one thing, but knowing that you need to do something about something and choosing not to, that's called acceptance. So, anyway, that's something to think about. Have comets impacted the Earth? Yes, they have. Roughly about 12,000 BC, we had, in fact, this article actually just came out this week. There was an impact over the Atacama Desert, roughly about 12,000 BC. This is in the Younger Dryas period, or Dryas period. There's about a 47-mile swath of the desert that's famous for these dark glass rocks that have been formed. And a recent NASA study, which was actually released this week, actually showed that those items of glass actually hold meteoric dust and small rocks. So again, NASA's conclusion was that there was a comet roughly about that time that actually, exploded over this region, creating this unique formation of glass silica. Now, that's the thing about the Atacama Desert. Now, we don't know what it looked like before the impact, but this is a pretty dry and arid area of the world. There's not a lot of life here, at least currently. We don't know what it was like before the comet exploded, but it's geologically it's unique because it's really in the shadow of two rain droughts. So there's two ranges, and basically anything that's basically on the wrong side of both of those ranges. So it's a really dry area. So probably not a lot of life was there. However, about 2,000 years later, there was another cometary impact, which we think now occurred in Upper Canada. And what it did was it actually propelled ejecta out of either Canada and actually impacted here in North Carolina. So if you've ever heard of the formation of Carolina bays, these are very unique because they are deep on the southeast end and shallow on the northwest end. So it's much like if you had a projectile coming in at an angle and bearing in like this. They're all oriented, by the way, in a more or less northwest to southeast formation. These Carolina bays have water in them, but they have no tributary streams. So it's very unique. This is a unique geologic structure that was actually discovered in the 1920s. And so they're all over North Carolina, but we've actually discovered them like in upper parts of Minnesota and other places in the United States. I'm not going to go into a lot of it, but we do know that roughly about that same time that these bays were formed, that we also found that we had the disappearance of woolly mammoth in North America, and also too the Clovis people, which were people that existed from Canada down through the South Carolina region, also went into decline and later became extinct. So it also created another mini ice age, which lasted for about 700 years. So it did have a huge effect. Again, many people, believe, it's a thought that this was a comet impact, not an asteroid impact, that actually caused this to occur. So we can talk about that a little bit more in the questions later on. So it does happen, with it being, roughly over 10,000 years ago, roughly, or 12,000 for us now. We're kind of due for something like that. So again, getting those technologies and deploying those technologies to do something about that would be really good. All right, so now let's go back to our next denizen in the solar system, and that is near Earth asteroids. Now, I got to tell you that when I was growing up, we didn't know of many near Earth asteroids. There were just a few. Icarus was one. And then there really weren't many others. And then really in the 1990s, we really began, especially after we experienced the string of pearls. NASA said, you know what, we better start looking out there and start seeing, well, what is it that's really out there around our Earth? So this video we're about to see, and I hope that this actually starts up here. There we go. I'm going to kind of like help this along. We began really roughly about in the 1990s, and this is a shot here in 1999, looking at how we were develop, where they were, and literally these kept continuing on and on and on and on. And you can see as we get into 2018, all of a sudden there are a lot of near Earth asteroids. Now the unique thing about Earth and its orbit is that Earth rarely and almost is never where these asteroids are. In a sense, we have somewhat cleared out our path. Now it's not clean, but generally there is never an asteroid where the Earth is in our orbit. So it is interesting, and you can see here that we've actually this is actually us with the asteroid belt here out here. There's a lot of near Earth asteroids around us. Again, we have no technology. We have no deployed technology right now to deal with anything. If we knew that there was an asteroid coming today, there wouldn't be anything we could do about it. In fact, this has happened a few times in our very recent past that we've had asteroids impact the Earth, and I'm talking within a few years, that have, we just kind of dodged the bullet. So we've been lucky to this point. But for those of you who would like to track this stuff and lots of other interesting things, there is a website. Many of those who have been in the club for a while know about this, especially those who are like sunspot hunters and those who are looking for aurora. On this side of the page, we've got all sorts of great sun data about what's happening with the sun. This is, again, spaceweather.com. Just look it up. It's a great site to go to. And you can also, if you see here, this little thing that says archives, you can look at the space weather for almost any day that the space weather website has been alive. And it's been alive since the mid 90s. So you can use a lot of data out here. But what's really cool about space weather is they also talk about what are the near Earth asteroids that are coming by, recently. Now I did this one back in 2019, and all the ones that are kind of outside of the universe, or outside of our solar or of our orbit, pretty far, they label in white, like they use the term LD. Now LD is a lunar distance. That's roughly about 248,000 miles, which is roughly the average average distance that the moon has from the Earth. That's called a lunar distance. We also call that the lunar veil, because anything that goes in between the Earth and the moon, we say, is piercing the lunar veil. So the moon is really our last bastion of defense against incoming asteroids. If you really track these things, you'll see that the moon really does change the orbit of these asteroids as they're whizzing by. And most of the time, it either again takes it on the chin, that's why it has a lot of craters, or basically deflects it away. What I wanted to do is I kind of highlighted over here on the right, this one here, 2012 DA14 on February 15th. It had a pass by of 0.09 lunar distances. Well, it actually impacted Earth. This was the famous Treblinka asteroid that impacted over Treblinka, Russia, Siberia. And I don't know, many of you may have been around, you saw that. It actually was about roughly 27 feet long, roughly about the size of a school bus. It came in. We were actually looking at another asteroid that was passing by and didn't look the other way. And this one actually came in from the other side of Earth's orbit and impacted the Earth. And when it actually went over Treblinka, it actually exploded. It exploded very high in the atmosphere, which was lucky for them because it literally was had the force of a small nuclear blast. Now it kind of blew out windows, startled a lot of people. Chunks of it kind of fell in a nearby lake, but it didn't really harm anyone. Unlike the Tunguska event, which happened in the early 1920s, that is theorized to be an asteroid that was a bit larger, but actually made it further to the ground. And it could have been that it was composed of more dense material, and so it was able to make it closer. And that literally leveled an area in Siberia, roughly about 27 square miles. So it was, it was very destructive. But at that time, there was relatively few people in the world living there. So we don't really know of any casualties. except from some of the locals that lived around there suffered, intense burns, intense heat, from that. But so anyway, these asteroids do have really destructive power, and literally on the order of a nuclear device, without all the radiation. So it's really important again for us to really develop technologies to knock these guys out, or at least deflect them away from the Earth. And of course, in the next slide, we've got, of course, the big one, which was the Dinosaur Killer, roughly about 65 million years ago, that actually struck off the coast of Yucatan. And so this is basically the where it's supposed to be. If you look here on the left, and then on the right is basically, like, I guess, a lidar of the area where you can actually see the crater that was actually formed off of Yucatan Peninsula. It's actually underwater, so you really can't see the entire crater. You can see on land some of those crater remnants, but again, erosion on the Earth has actually caused a lot of the crater impacts that we have on Earth to have been eroded away, and that's why, on the moon you see these great craters out there. That's all that good cratering and everything, because there is no atmosphere to erode away the crater. But on Earth, many of them have. But this is the one. This asteroid was considered the one that actually caused life to really nearly go extinct, killed off the dinosaurs, allowed more of the mammalian creatures that were able to adapt to evolve to higher species. So anyway, we're overdue for an asteroid impact of this type. And so again, it really behooves us. You have to ask yourself, well, gee, if we've had all these years of evolution and all these years of great thinking and everything, and we still haven't been able to produce a technology to deflect and deal with asteroids, how much have we really evolved from the dinosaurs? That's a question we have to ask ourselves. If we're still not able to deal with that issue, and the next one that comes in and wipes out mankind, all that evolutionary work and everything was for naught. So it's just a thought. All right, so I'm going to get off the asteroid and comet soapbox, and we're going to go to dual Chrono Mass ejections. This is one of my favorites, and I know that that we've got a few folks in the club that are actually imaging some really great solar flares and solar prominences right now. Mike Mantini is doing some great and fantastic work. So anyway, but sometimes these things can happen, in a double burst. Now, what's interesting is that the Earth has a really interesting relationship, and our magnetic field is so unique. It really is unique in our solar system. There's really not another planet that has a magnetic field like Earth. We know some others do have magnetic fields, but some of them are really quite strange. Especially Jupiter's is really quite odd. But anyway, ours really acts as a great shield. Now, there's some components to think about. We have the sun here, and the sun is supermassive. The sun is so large that the sun really contains about 98% of the mass of our solar system. So if you just think, if you had $1,000, then $998 would go to the sun. $1 would go to Jupiter, because it's 1/1000th the size of the sun, and then the rest of that $1 is spread out among the rest of the objects in the universe. So that's how massive our sun is. Our sun is super massive. So it's huge, but there we have this really interesting relationship. We are just really at that right place where the solar radiation is able to warm our Earth without incinerating our Earth. And of course, we have to protect us this really amazing magnetic field that you see here on the right. In between us is this really odd goopy mixture called the interstellar medium, or the intersolar medium, however you want to call it. And it really serves to slow projections and ejections from the sun. And we call, again, when you have a solar prominence and it breaks and it kind of flings matter out from the sun, and it heads towards Earth. This inner solar medium literally is again molecules, atoms, particles that are they just sit there and they kind of slow that down. That gives us time to get out of the way. So it's this interstellar medium, intersolar medium, whatever you want to call it, actually does work to protect the Earth. Well, let's move on here. Again, I'm showing this. Our magnetic field is working here. We have a lot of charged particles over here on the left side of the screen streaming in to the Earth. These charged particles often get deflected down to the poles. That's where you see these dips in this magnetic field. And then over here on the right, these is an actual a picture of a coronal mass ejection that hit Earth 13th March 1989. One is in the north, or sorry, the first one on the left here is the south, and then the next is in the north, in the northern region. And of course, this one actually caused a lot of blackouts and stuff. It was a lot of high energy and everything in this one. But so these coronal mass ejections, if they hit and they basically can be picked up by power lines and transmitted to power stations, they can actually cause explosions at power stations, which cause blackouts and all kinds of angst. Now, this is the one on the, we're just looking at, if you can barely see it, it's not very good, but this is kind of superimposed. This is the map of the United States. And when the coronal mass ejection hit, it actually hit mainly in the northeastern and Canada, northeastern United States. And it it caused a series of rolling blackouts. And so we had blackouts all along the eastern seaboard and into the northern east portion of the United States. Had a little bit up in the upper Washington, Oregon area, but the main part of that was actually here. Now, the reason why this is we have power lines strung all over the United States and also in Canada. And when you get all these charged particles raining down on the Earth, it can actually cause the Earth's magnetic field to collapse. And when that does that, those power lines are out there and they're acting like massive antennas, and they actually receive, just like an antenna would on a house for receiving a TV signal, we receive all that energy going along those lines to the next substation or to the power generation plant. And they can literally cause high tension transformers to absorb all that energy and then explode. And then it's then when those explode, it takes a long time to replace them. So these blackouts can last for days, weeks, months, even years. Theorized. We haven't had any that lasted for years or months, but we've had them last for days. And I'll tell you why in just a minute. So that was just one coronal mass ejection. But in Earth's history, we have actually had a dual impact. Now, it used to be thought that there was only one dual impact, but there's been some sleuthing over the last few years, and we've discovered that these dual impacts do occur on a more regular basis than we thought. Now, the big one was in 1859. It was known as the Carrington event, and that's named after an astronomer, Carrington, who was looking at the sun, observing the sun. Over on the left here, he actually did a sketch, a very nice sketch, by the way, of this sunspot. And then he basically saw a flare occur right about that time. About 3 hours later, there was another one. Now, what happened with this flare was it created a coronal mass ejection that pushed it out towards Earth. Now, it took a few days for that coronal mass ejection to come. And that's mainly because it was kind of pushing that interstellar medium out of the way. But the one that occurred right behind it, about 3 hours later, followed very quickly. And so the first one cleared out the interstellar medium and left Earth, basically kind of collapsed Earth's magnetic field in the process. And so basically Earth was left wide open. And this thing hit the Earth. The second one hit the Earth, causing aurora to occur all the way down to Cuba. So it was really massive. But the thing that it was really telling is that our newly formed telegraph system at the time, we didn't know about isolating electronic equipment, and so those particles and all that energy rained down on the telegraph system, and went down the wires to telegraph offices. Telegraphs began chattering without anyone doing anything to them. And then a lot of times the telegraph offices just burst into flames and exploded. There was so much energy coming down the wires. So this lasted for about 9 days straight before Earth's magnetic field was able to kind of, re-resurrect itself. Now, the idea that if that happened today, it would be much more catastrophic because we have a much more highly developed grid, not only in first world countries, but also in second and third world countries. And so, first world countries have been studying this for a while, and electric companies have been working with NASA. So hopefully they're prepared. But if they're not, what could happen is that, again, these high tension transformers could be affected, melt down, and explode. Now, we only have roughly about 12 or so of these high tension transformers actually in reserve. So if you lose more than 12, you got to wait for them to be built. The idea is that, look, if we get one of these massive ejections, we could run out of power and not be able to power the Earth for about 12 years. So there is a real possibility for something like that. So it's important to keep a track on. But again, probably for first world countries, this may not be an issue, but for second and third world countries that actually are not working with NASA with this, it could be a real problem. All right, I'm going to go on to the next one, UVA and UVB radiation. So basically, I'm not going to go into the anatomy of the sun because we're running short on time, but basically we have the sun generates UVA and UVB radiation. Many of you know about it because it actually creates. This is the radiation that creates sunburns. If you look, and I do want to talk about this for just a minute. If you're looking at the sun, and this again unaided, you don't have to have binoculars to look at this. If you just look at the sun unaided, you can develop a solar retinopathy. And so on my left here, we have a healthy eye. It's in good shape. We have the optic nerve over here. We have the retina. And then on the right, we have an eye that has been exposed to the sun. And you can see that around the retina, there's a lot of blistering. And so, this can be a permanent, this can permanently damage your eyes. Some people, it just depends on how much your exposure is. Sometimes you can get a case and you can recover from it. But you can see, the optic nerve is really inflamed over here on the right. Of course, the retina is really, really blistered around here. You can see the blood vessels are basically, again, they're enlarged because they're trying to dissipate all this heat, so they're dilated. So this is a really bad situation to be in, and this is really just from looking at the sun. So I know there are a lot of people who kind of like to kind of just see how long they can look at the sun and as it rises and everything. Please don't do that because you have a lot of, we're not really genetically engineered to take a lot of energy into our eyes. So you really need to make sure that you protect your eyes. I'm going to say that your sunglasses help a little bit, but they cannot stop totally UVA and UVB radiation. The only thing that you can really use is like a Mylar filter that can really filter out, 99.999% of the radiation. So really be careful at looking at the sun. It's really important. I definitely, with a telescope, a pair of binoculars, or even a toy pair of binoculars from the like say Toys R Us or something like that. Do not look at the sun with those. You can literally obliterate your eye with that. And I don't know if Steve Goodman is on the call tonight, but I'll never forget. Steve actually really gave me a really good demonstration of this about 20 years ago at an astronomy days. He had his telescope pointed towards the sun, and he put one of those old film caps over his eyepiece, and he took his solar filter off of the front of his telescope just for a second, and literally I was looking at the film cap, and it literally blew a hole in the film cap. in just like a few milliseconds. So looking at the sun with your telescope or with, even again, a toy pair of binoculars, don't do that because you literally can burn your eyes and burn them out permanently. So you don't want to do that. So it's really important that you really pay attention to UVA and UVB radiation as it's coming from the sun, as it's entering your eyes. Okay, that's very important. That's another reason why during a solar eclipse, as we're coming up towards the eclipse, you want to make sure that you're wearing glasses or something like that to protect your eyes, because your eyes will begin to dilate, but it's there, the UVA, UVB radiation is still streaming from the sun. So you don't want to receive all that into your eyes. Next, of course, sunburns are bad. Skin cancer, skin cancers can occur. Very dangerous because this is a light case. We've been able to capture the skin cancer early with early detection. But if you don't really take care of that, the skin cancer can actually grow through your skin cells down into your bone, and it can enter your bone, and you can have a bone cancer from that. So you really don't want that to happen. So it's really important, of course, always I'm going to say, go to your dermatologist on a regular basis. You should be getting a regular dermatology exams. Also, make sure you use SPS 50 or better. Don't be like these guys over here on the left and get burned like that. It's not a good idea. All right. Let's go on. So we'll talk about super flares. Now, this has been one of the sci-fi spoofs that's kind of come out saying, hey, what if there were a super flare and it struck Earth? And this is actually a large flare that occurred on the sun, roughly about 2003. NASA took this photo and basically superimposed Earth, which you see over here in the lower right-hand corner, by that flare. You see that flare was much, much larger than the Earth, and had the Earth been there in that path of that flare, it would have incinerated the Earth. But the thing that's great about solar flares and stuff is that, and you can actually see some of Mike Mantini's work and the work of other people like Chris Cole and others who have taken some really cool pictures of prominences and stuff. You can see these structures. These are really cool structures. You have magnetic fields that are kind of pulling these. You see these lines of flux, and it's pulling this plasma from one magnetic pole down to the next. But sometimes they snap, and when they snap, they fling out material and from the sun in the form of a coronal mass ejection, and accompanied by all this energy that we call a solar flare. The thing that's unique about the solar flare is it's kind of like running into a room with a lamp that's plugged into the other wall. The moment that you pull the cord out of the wall, the light goes out. And that's really kind of what happens with solar flares. Once they kind of leave the sun, they quickly run out of energy, and the Earth really is not in danger from the energy that was once in the solar flare. Now, we're still in danger from the material, the coronal mass ejection, that could hit the Earth and collapse our magnetic field, like I said in the prior slides. But in terms of super flares themselves, we're not that close to the sun. And so we're not really in the path of where we could be hit by a flare like that. So we're in pretty good shape. So there's not much chance that could happen to us. I'm not going to go over this piece. We can basically, the sun does produce a lot of flares, especially during its the sunspot cycle. We're actually getting into solar maximum. We're heading in that way now. So you're going to see a lot more coronal mass ejections, some more energy being flung towards the Earth. At peak times, we could have as many as 20 flares a day. But again, we're far enough away, it's not really going to hurt us. All right, I'm going to go on to the next one. All right, so then the other thing that we have to worry about now is space junk. So when I was growing up, there were only few launches, and so we didn't have as much space junk to tend with. But unfortunately, over the years, as satellite launches have increased, we have a ton of junk around the planet. Now, some of the space agencies now are being more conscientious and making sure that their booster rockets and stuff like that are actually deorbited back to the Earth after they deploy satellites and stuff. But still, you get satellites up there that stay up there for years. Some of these things, we still have booster rockets that are floating around from the Apollo era, still moving around. Here's some examples of some stuff that actually just made it back to Earth. So if you're standing under one of these guys when it actually hits, that could be a very bad day for you. But there's a lot of junk raining down on the Earth. Routinely, Earth sucks in about 20 tons of material daily. Now, the thing that's good for us is 76% of our planetary mass is covered by water. So most of this stuff falls over water. And then really, we don't have that much of our land area that's actually populated right now. So what makes it back to the Earth generally falls in an unpopulated area. You can see these guys out in the desert and everything. They've been able to find basically a fuel tank. But yeah, so we're in not as great a danger as that. So, but it is something that we really do need to clean up our space junk. I just read an article actually yesterday that the International Space Station is having to prepare to lift its orbit because of a piece of space junk coming from a Chinese demonstration that occurred a few years ago, and so they're having to kind of dodge that space junk. All right, we do right now. We don't have any deployable technologies that are dealing with it. We do have some on the drawing board. Again, this is one of the things we've known about for years that we need to deal with, and we're not dealing with it. So it's just, again, something we need to deal with. All right, let's move on. Earth's magnetic field is changing. We know that it's moving. It's actually becoming a bit more weak. It's beginning to prepare for a magnetic field pole flip. We haven't had one in about 300 years. 300,000 years. We're right on time for that. We can see that it's demonstrated that it is moving. The next slide, we can actually see that it's moving about 1 kilometer per year. So it's actually moving south. It passed over the north I think in 2019. It's actually now headed south. And so it's headed south more into, into Siberia, upper Siberia and everything. So this is what's happening. Interesting article. So there is some evidence that there was at the last pole flip that we actually had some extinction and everything. It's hard to say, what's happening. It looks like I lost my note here. Extinction of large mammals also occurred around that time. In Northern Europe. This has actually been verified in a recent study, and so it's pretty interesting to note. Before, people believed that there were no extinctions associated with pole flip, but now we know that there are. It's hard to say what's going to happen. We're just going to have to cross that bridge when we would come to it. We are very adaptive, and hopefully we'll be, Earth's life will be able to adapt to that pole flip as it has for, thousands of years or hundreds of thousands of years. So. Anyway, so it'll just be something we have to watch for. All right, so I'm gonna go to the next slide. There we go. All right, so the next thing I want to talk about is something that we can do something about, and that is global warming. So these photos I have right here are really from last year, from 2019 or so 2020. And so, of course, this was when San Francisco was bathed in with fire and smoke and stuff like that. Of course, this past year was just another banner year. So I just to let you know that just in California alone, okay, and this is not the other states, because other states are also dealing with wildfire. It's getting bigger. Every year we see more acres burned every year. This past year in 2020, we don't have the 2021 stats out yet, but in 2021, I mean, we went from 5.5 acres into 5.5 million acres in 2016, which was considered a banner year then, all the way up to 10 million.1 acres in 2020. So, we are having, there is a real effect of global warming actually driving these fires on our planet. And especially in our northwest states. Some other things that are occurring: storms are literally becoming more intense. This is the derecho of 2020. And what happened with this derecho was right here in the middle top panel, you can see that the corn fields of Iowa were literally, they lost a tenth of their corn crop. So it was basically their cornfields were decimated in about 3 hours just from this derecho, which is basically a tornado that's turned on its side. And so it literally, again, in 3 hours, wiped out a tenth of the corn crop. You know, had it been a more intense storm, it could have been much worse. Last year, in 2020, we went all the way through the Greek alphabet, and then we had to start numbering them. So the storms were hurricanes were much more intense. Fortunately, this year it doesn't look like we're going to make it that far like we did last year, but still, you know, quite an active hurricane season. If you look right down here in the lower left-hand panel and see this really nice canal here, well, this was actually I-40 on September 15th, 2018. So this was when Hurricane Florence hit North Carolina, and it was just a tropical storm, but it stalled. And when that stalled, it brought torrential rain to eastern North Carolina. Again, this is you can see the overpass in the far right here, far in the far ground here. This is actually I-40. It's not a nice canal. It's I-40. And so a lot of eastern North Carolina was underwater. I had personal friends that lost property, lost homes in this deluge. I myself was out in my front yard digging a trench for my daughter's wedding when it hit. So it was literally 2 hours before the wedding. I was digging a trench to get water off our driveway so my daughter could get married and guests could arrive. And then over here on the right, we see ice shelves, and the ice shelves here in Antarctica are beginning to break off. And we're not just talking about, you know, just a small little ice shelves. We're talking about ice shelves that are the size of Manhattan, that are breaking off, you know, and scurrying off into the sea. The thing about it, you know, Antarctica is that this is ice over land. So when it breaks off, it actually adds to the level of the sea, and our sea levels are rising. There was there's an island, a small island nation in the South Pacific, and there is a Welsh community up in northern in England. That both of these communities are now being wiped out because of sea level rise. The other thing we have with glacier melt is we're losing all the weight that the glaciers put on our Earth, and so our Earth is turning from an oblate spheroid into a sphere. We're actually beginning to pop up. So we don't know what that's going to cause, but probably more uniform warming over the entire surface of the Earth, because you're now looking at warming a sphere versus an oblate spheroid. So there's a lot of issues here. Again, 3,000 glaciers can't be wrong. Something is really going on here. So I'm going to just show you right here. This was an actual predictive map from a climate scientist in the 1980s, James Hansen. And in this predictive map, you can see the black line is actually actually what was occurring at the time. And then we have this predictive map that goes from about 1988 all the way up to 2019, and this is how far he predicted it out. Now there are three scenarios here, and what he did was he was actually looking at greenhouse gases. He was looking at carbon dioxide, he was looking at nitrous oxide, he was looking at methane, and then he was also looking at the CFC 11 and CFC 12. About 1990, he predicted that we would be diverging with respect to these two scenarios down here, but that this warming due to carbon in the atmosphere and methane would continue. Now, what's interesting is that there's been a lot of talk about, well, hey, isn't global warming really being driven by Earth's eccentricity, its precession, and its tilt? There is a little bit of drive to that. These are called Milankovitch cycles for those of you who are glaciologists out there. But as he began to look at this, he predicted that really the Earth warming with respect to the solar radiance would not be a factor. So the question is, was that a factor? Again, this was him making the prediction in 1988. Now we look at let's fast forward to 2020. And here we have over here on the right, his same graph. Okay, but this now is actual graph. And we can see the bottom graph, the bottom line is really the effect of climate change with respect to solar radiance. Well, what's really funny is that in 1990, 1960, we began to diverge from that. And it's actually fallen over the years. So climate change being driven by solar radiance is really not relevant. But climate change due to the release of carbon dioxide, methane, nitrous oxide, into the atmosphere has grown. And look, I want you to see that he's grown to what roughly almost that 1.5 degrees that he predicted would occur. So we're really at that 1 degree mark, very close to the prediction that they predicted back in 1988. So this is just, so now we have the empirical data. Before we had predictive data, now we have empirical data that shows that the unrestricted use of carbon and methane and release of that into the atmosphere is driving climate change. Now, this is something we can do about that. It's same thing with the asteroids and with the comets. We have the technology, we have things that we can do about that, but we are not doing anything with that. And we're just choosing to accept it as normal. So we're going to continue to see sea level rise, more powerful storms, more electrified storms, more intense wildfires. These things are going to continue to occur, and we're going to reach a tipping point, though, where no matter what we do, we're not going to be able to turn it back. So it's really important that we do, no matter what side of the fence you're on politically, that we really all kind of need to get aligned and actually get behind the empirical data and really begin driving our elected leaders to support, supporting legislation that will do something about this. All right. So finally, the very last thing is that our own sun will at some point in time, really in about 4 billion years, will have expended enough of its mass that it will no longer be able to attract its outer layers to its inner layer. And so that outer layer will begin to expand. And we call that roughly, the red giant's phase. Our sun will become a red giant. And that red giant is theorized is going to be so big that it could actually expand to Earth's orbit. Now, the question is, what's going to happen to Earth? The answer is we don't really know. It could expand to the size of Earth's orbit, and if Earth doesn't get out of the way, then Earth will most likely be absorbed by the sun. We'll kind of cook in that outer 800-degree layer that will kind of envelop us, will eventually dissolve and be destroyed. Or it could be that as the sun's mass, as it loses mass, because you remember the sun is converting mass into energy, right? E equals mc squared. So it's basically converting mass into energy, and it's consuming that energy is actually radiating out into space. Most of it we don't even use, but it's radiating out into space. And so once we lose enough mass, that it's going to begin to expand outward. And we won't end in a supernova, but we will end in a nova. And that nova will produce many of these beautiful objects that we actually observe in the night sky. These are all examples of planetary nebula, where these are star-like or sun-like stars that ran out of fuel. And so their outer shell began expanding and eventually sloughed off in a nova event and began expanding like this. And you can kind of see the shock wave of that nova event right here being illuminated. It's actually being illuminated by the solar wind coming off of the central dwarf star that's now becoming a fission star rather than a fusion star. But the solar wind is irradiating these outer cloud of nebula, causing this nebula that we can see. The Dumbbell Nebula is also an example of one, but we're just looking at it from the side versus from the front. So Roughly, this is going to happen in about the next 4 billion years. Not really a lot that we can do about that, except get off this planet and find another place. We need to be out there exploring the cosmos, and hopefully we're going to continue doing that. But anyway, so that's really the kind of the conclusion of that of the talk. And that's really a kind of our deadly spheres. So I'm going to kind of open it up now. I know I kind of went long, but I'm going to open up to any questions if any of you are still awake out there.
Thanks, Doug. So yeah, I've got a few questions that were posted in chat. First one was a question, a bit more on the solar system itself.
Yeah.
There's a question here, that they heard that the solar system is approximately 2 light years across.
Yeah, here's the thing. We really don't know how large our solar system is. If you go back to that graph that slide I was looking at, it on one side it looks kind of it looks small, and the other side is kind of spread way out. We don't really know how large our solar system is, or the thing is we're defining the solar system as where the sun's influence ends. And then we know that there's kind of where it's orbiting there. It's shorter. There's a bow shock there. There's the heliopause and stuff like that. So yeah, I don't know. It's possible. It could be. At least what I read, it's theorized roughly about 100,000 AU. That's somewhere within about 0.3 light years. But it could be. I'm not going to deny that. It could be.
Okay, very good. Okay, had another questions and comments, or question and comment. I think when we were talking about the Carolina Bays, it is just really a worthwhile place to visit. I have personally been out to Jones Lake State Park. Great place to camp. Also a really neat place to just kind of check out. So yeah. Last question in the chat is, what is the difference between an asteroid and a comet?
That's a loaded question, because we have the thing is we have asteroids that behave like comets, and we have comets that behave like asteroids. And so I'm going to set it as this, that you're going to have a completely rocky object is going to be an asteroid. Comets are really amalgamations of silica, clays, and other bits of material that have had kind of like just stuck together, and they're
Dirty snowballs.
Dirty snowballs. Thank you. That's exactly what a lot of people describe them as. A lot of scientists describe them as. And so they're very different. Now, the thing is that we do have a few objects that kind of cross that line. So we've got some asteroids that when they near the sun, they develop a coma, some of them tails, but they're asteroids. And that means that they have silicas on the surface that the solar radiation is heating, is interacting with, causing them to heat up, to outgas, and to kind of display comet-like behavior, but they are asteroids. Same way, it's theorized that comets only have so much material on them, and the number of times that they've made it around the sun, they kind of, lose that ability to develop coma and develop tails. And so it's thought that those comets that are able to do that have actually been around the sun a lot of times and are very old, but they've lost that ability to actually generate a coma and a tail. So a coma and a tail does not make an asteroid, or does not make a comet. It's really the composition of the object, and just like Mike said, the kind of the dirty snowball composition, lots of water, ices, silicas, clays seem to make up. Again, it's more of a and loosely amalgamated rock versus an asteroid which appears to be chunks of rock kind of left over from the formation of the solar system.
Yeah, and I think it's become very much, where it used to be thought that there were, completely separate objects, and what they're finding is you're really looking more along a spectrum of things where you've got, your traditional asteroids on one end of the spectrum and your traditional, dirty snowballs with, a nice coma and tail and everything on the comet side at the very other, and lots of stuff falling in between.
Mhm.
So if folks want to come off of mute and ask any other questions for Doug.
I did see a comment in there about the primordial black hole having about 5 to 15 Earth masses. Wouldn't that destroy the Earth? You have a point there. I think Steve asked that question. You have a point. I'm just, again, based on the articles that I've read, it appears that it's small enough that it doesn't cause that interaction, but basically it just passes through the Earth, or it causes, or like I said, it could get lodged at the core and literally consume the Earth. But yeah, I mean, I don't doubt what you're saying. Anything that's 5 to 15 Earth masses seems to me, I agree, would gobble up the Earth. But again, according to the articles that I read concerning that, they didn't really bring that out, unless it, like I said, unless it got stuck at the core. So
I think it would shred it on the way in.
yeah, I mean, yeah, I don't know. I'll tell you, maybe Steve Christensen is on the line and he can explain that to us a little better.
Well, if you look at the orbital dynamics of something that's much bigger than the Earth, if it comes even close to the Earth, it's going to cause it the orbit to be disturbed and the spin of the Earth to be disturbed. And I mean, the moon was formed by a smaller object than that, hitting the moon and basically creating 2 new bodies. So a black hole of that size is going to be a major disturbance. But it won't really, it doesn't have much to do with the fact that it's a black hole, just that it's small. I mean, it's not going to, something that small is not really going to absorb much. Okay, it's too small. The surface is too small. Mm-hmm. So, and the picture you had of the Earth being spaghettified, that doesn't happen that way either. Okay. So
it's there for shock value, but yeah.
But that wouldn't happen that way.
Yeah.
Yeah, I mean, a supermassive black hole, the black hole's gravitation now it's not that great. So you're not going to get spaghettification. It's the smaller black holes that are more dangerous in that regard. Okay. So the big black holes, you could be in the black hole and not even know you're in the black hole because at the surface of the black hole, the gravity isn't really that strong. Mm-hmm. So it's way more complicated depending on the kind of black hole. And we don't know if there are any primordial black holes at all. We haven't discovered any of them yet. And you're not going to discover any black hole by Hawking radiation, which is still a theoretical construct. And no one's proven it exists. So it's put out there as a fact, but it's not a fact. It's a theoretical construct. So.
Well, good point. I'm going to update my slides to kind of.
I'm happy to talk to you about that.
Okay, that'd be great. Yeah, that would be a good talk to have. I'd like to know more.
I think I read something like even a stellar mass black hole, the Hawking radiation temperature is like 0.01 Kelvin or something. It's like ridiculously low.
Not at all. You have to have a much smaller black hole for it to give off much radiation. It's an insignificant thing. So,
okay.
Yeah, something that would take, stellar mass black hole is going to take trillions upon trillions upon trillions of years to evaporate.
Exactly right.
And we're only, 13 billion into into our.
No, I worked with Stephen on this stuff back in the 70s, and we never imagined it would get this much hype because it's really hype. It's not that significant.
Cool.
Any other questions for Doug? Okay, well, with that, Doug, thank you very much for
Thank
a
you.
great presentation. And I appreciate you doing that.